So this is the last Game Maven assignment, and this will also be the last Game Maven tutorial to get us ready for the test. I'm going to go through lessons 1 through 60, and I'll try to go fast through some of the parts that are basically review. All right, so they're just starting us off really simple here with quick review and a small little rectangle there in the middle. The only thing to kind of refresh our memories about here is why they do the w minus size over 2 and the h minus size over 2. And actually, explains that she explains that pretty well in the next slide. So the next few slides. So we're going to skip quickly here, all this stuff here. And it says W and H are the width and height of the canvas. X and Y are the top left corner of the square. Size is used for the width and height of the rectangle, so it draws a square. Now here, let's answer the question of why lines 4 and 5 are coded as they are. You see why the square will always be in the center. Try changing size to 40, etc. So let's change size to, I don't know, let's do 80, or let's do 120. We can see that it's always centered. And here's why, okay? The reason it's always centered is because if you are going to, let me go back just a second. It says half the width and half of the height is the center of the screen. So let's say for this particular one, 120, or let's make it simpler. I'm gonna do 100. Okay, so if size is 100, and we remember that the width of the screen is like 400. If the width of the screen, or the width of this canvas here, the canvas is the right hand side square. If that's 400 pixels, well, 400 minus 100 is 300, and so that would put me at about here where my mouse arrow is, right? And then divide that in half, and you have this spot here. And this spot here is the top left corner of the square. This would be the x coordinate of that top left corner. And then h minus size divided by 2. If the height is 300, well, then 300 minus 100 would put me here. Half of that brings me to the, again, top left corner, the y coordinate of the top left corner. So that's how we would center each square always around the center of the screen. Okay, let's skip through some of this. The first game we're going to build is a little space-based defense game. We're going to start by drawing a base, then do some animation for shooting lasers, then make some enemies to shoot. It's going to be great. You can see where we'll be going. Here's an example of the kind of thing you will be building soon. There will be animation, movement, rotation, collisions. Lots of fun code in a game. All right, well, this particular screen is completely review of Code Maven. There is absolutely nothing new here. But I thought it would be a good idea to do a quick run through of the code as a preparation for the rest of this video. Okay, so box size just determines the size of the box. Num boxes is the number of boxes. I can change this. I could do 20. I could do 30. I could do 90. And it's very easy to control the number of boxes. But let's keep it at 10 for now. Now, lines 4 through, I'm highlighting. So lines 4 through 42. Look at that big chunk of code that I highlighted. Lines 4 through 42 simply define a box object. They define a box object. And so if box is the type of object, each one of these 10 boxes is an instance of the box object. That's what we call them. We call each box an instance of the box object. And the box object receives these parameters, x and y, which are the x and y coordinates, size, the size of the box, a, which is the initial angle, and then dx is how much the horizontal coordinate changes, dy is how much the vertical coordinate changes, and dA is how much the angle changes. So these last three parameters determine the horizontal and vertical speed as well as the angular velocity of the box. Okay, all of this stuff which has this, okay, this just means that for this particular instance of box, this is the value of x, y, size, angle, dx, dy, and dA. Now, um, what does this mean? Well, to understand what that means, we have to kind of go down to this for loop and look at what's happening here with the for loop, okay? Um, what's happening here is we are creating new boxes, okay? So what I've highlighted here is the line in which new boxes are created. New box x, y, s, a, dx, dy, dA. Well, the for loop runs 10 times, and each one of those 10 times, the variables defined in line 62 through 67, which I'm highlighting now, those are different each time since they're randomly being picked. And so the x, y, s, a, etc. for one box is not the same as the x, y, s, a, etc. for another box. Now, line 4 simply takes whatever parameters are sent it, and then lines 5 through 16 and all the way to 17, they take those parameters and they make those parameters their own. They're saying, okay, this x is the x that I just received. This y is the y I just received. This size is the size I just received, etc. Okay, bouncing off the edges, we saw that in code Maven. If this dot x is less than s over 2, because s over 2 would be half the size, and we're saying that the bounce should occur when it's within half the size away from one of the walls. Okay, so if this dot x is less than s over 2, or this dot x plus s over 2 is greater than w, okay, all this means here, which I'm highlighting, is uh, a left edge bounce, and all this means here, which I'm highlighting, is a right edge bounce. And if there's a bounce, you reverse the x velocities. Well, if there's a left or right bounce, you have to reverse the left or right, that is the horizontal velocities. So whatever's positive becomes negative, whatever's negative becomes positive. And you have to invert the spin. So if it was turning counterclockwise, it now becomes clockwise, or vice versa. Now let's talk about the top and bottom bounces. Okay, this dot y less than s over 2. This refers to a top bounce. And then the next one, this dot y plus s over 2 greater than h, that refers to a bottom bounce. If there is a bottom or a top bounce, you've got to reverse the vertical velocities. So dy becomes negative dy and vice versa. And you have to reverse the angular velocities. So dA becomes negative dA and vice versa. This dot stroke simply draws everything. And this dot stroke is a call to a function that is itself defined within the box object. And that function, the code for that function, is in lines 32 to 41. And what it does then is it does save, it adopts the x and y coordinates, translates to those, rotates according to the angle, and then draws the rectangle according to that. Now, why the save and restore? We need the save and restore because remember what's happening with rotate here and what's happening with translate is it's going every time from the top left corner for translate, and it's going every time from the top left corner for rotate. But see, if you don't save and restore, well, your new starting point is going to be wherever you did translate to the last time, and your new beginning angle will be whatever you rotated to the last time. So it's like, remember, stroke is doing this for all 10 boxes, and it's doing all 10 boxes many times per second, but it's doing them so fast that it all seems to be happening simultaneously to us. So when stroke gets called, it's only getting called for a particular box. If I don't do save and restore, I mess up all the other boxes. And that's why we need to do save and restore. Okay, and then the heart of animation is always with time step. That's the number of milliseconds. This means that every 50 milliseconds we're redrawing the screen. And that's, of course, controlled with CMTID. And then CMTID again appears in 54 and 55 with what we've seen in every single animation we've done. And all this says is call the function update all every 50 milliseconds. That's all this does. It runs the function update all defined in lines 49 to 53, and it runs that function every 50 milliseconds. Okay, so that's enough of a code Maven review. There's a lot of code, but don't worry. We'll walk through building each game step by step with lots of explanations as we go and plenty of chances to twiddle the code and experiment. Ready to start? First step is to draw the player's base. Then we'll make it shoot lasers and things to shoot at. Let's start with a base. Here's that box from before, centered right in the middle. Now here's another way of drawing that box, using a translate to move to where we want to draw it. Remember this from Code Maven? Comments explain how the code works. Okay, so I mentioned that a little bit in an earlier slide in this video. So we do the save and restore. If we don't do that, we mess up everything else. Now, notice here we're only doing one box to start out with. So save and restore really aren't necessary. But we're going to see why they're necessary in the next few screens. Because we use translate to move the origin, we now can use rotate to rotate the box around its center. From Code Maven, you might recall that rotate rotates around the origin and wants the rotation angle in radians. So pi is the same as 180 degrees. Here we are rotating by 30 degrees. 30 degrees is pi times 30 over 180 in radians. Okay, so that's just the conversion factor for how to go from degrees to radians. And then why the negative size over 2, negative size over 2? Well, let's look at where my mouse arrow is. My mouse arrow is right at the center of that square. Now, notice what has happened. In line 7, we have rotated the whole canvas. We have rotated the whole canvas, okay? And with the translate has said that the origin is now at the center. That's in line 6. All right, so line 6 brings us to the center. And then line 7 rotates the entire canvas around that because that center is now considered the origin. And so if I need to go left to the left and above the origin, well, that's negative because the origin would be the new 0, 0. What's to the left of 0? Something negative. What's above 0? Something negative. You've got to recall here, of course, that this isn't the same as math. In math, up is positive and left is negative. In JavaScript, with these computer graphics, left is negative, but up is negative, okay, and down is positive. All right, so negative size over 2, negative size over 2 means, okay, now watch my mouse arrow again. It means, and also notice how I'm going to be moving the mouse arrow. I'm going to be moving it in a diagonal way because since the whole canvas has been rotated, diagonal is straight. Diagonal is straight. Okay, so here we are at the center. We want to go left. Left is negative size over 2, and that brings me right here. But then we also need to go up. Up is negative size over 2, and that brings me right here. And now we draw the rectangle to the bottom right corner, which is size, and that brings me right here, okay? Because the whole canvas has been rotated. Can you add a second box to this? 2 boxes total right on top of each other. Make the first rotated by 30 degrees, next rotated by another 30 degrees, try to change the code to add that. All right, so take a moment to do that. You should challenge yourself and try to do this on your own. Pause the video and then resume when you have an answer. Let's use something like this for our base. It's 3 boxes, 2 of them rotated, like it. So look at what has happened here. We did the c.save, we did the translate, and then we did the first rectangle or square. That's in line 7. And then we did another rotate. Notice we didn't need to do a translate because we had already translated in line 6. And so what is 30 degrees away from the first square is the same as 60 degrees away from the square before that. Okay, or let's look at it this way. If the first square is straight and the second one's at 30 and the next one's at 60, we don't have to write 60 in line 10 because 60 is the same as 30 away from the last one, which was 30 away from the first one. All right, and this happens because we just keep doing rotates. Games need movement. Movement requires animation. Fortunately, animation is pretty easy. We just need to redraw the screen a few times a second. So that's what this does. This redraws the screen a few times per second. It does it every 50 milliseconds, and so it's redrawing 20 times per second. The initial angle is 0. Size is 80. We can change that. Maybe we want to do 200, much bigger. W and H still the same, CMTID. Now notice what's happening in lines 22 to 24. These 2 lines are the heart of every animation program, and they're always the same. This just says call the update function every 50 milliseconds. Now, what happens in update? Well, the first thing is you have to erase the canvas. c.clearrect00wh. That's from the top left corner all the way to the bottom right corner. Draw a box in the center, so we do the save, translate and rotate, nothing new there. And then angle plus equals 1 means that we're adding 1 to each angle. All right, we're adding 1 degree, and we're adding 1 degree in each frame of the animation. Can you speed up how fast the box rotates? I'm going to reset this because I already did part of that. Can you speed up how fast the box rotates? There are 2 ways to do that, either by changing how frequently update is called, or by changing how much the angle changes each time update is called. Can you do it? All right, well, again, pause the video, try it, and then resume when you have your answer. So you should have tried a couple of things. You could have changed time step, like let's say I change it to 10. And so if I change it to 10, that means it's doing this 100 times per second. You know, it's pretty impressive that the computer can do everything so fast. So it's doing this 100 times per second. Or let's bring it back to 50 and change the other thing they said, which would be the angle. Well, let's say that instead of increasing by 1 degree each time, I increase by 20 degrees. And now we can see how much faster it moves. Can you figure out how to draw that base we did earlier? It was 3 boxes, the second 2 each rotated another 30 degrees from the previous. Can you make a slowly spinning base instead of a slowly spinning box? Try it now. All right, another chance to pause the video and resume after you've done it on your own. Here's what I did. If you got something different, maybe you rotated the second and third squares by angle instead of 30. That creates a cool and fun effect, but this is what we wanted. If you rotate the next 2 squares by 30 degrees, like this code does, it makes a good base, a small spinning star-like object right in the middle. And what we have here is we have something that looks like a star, but really it's just 3 squares, 3 squares, one on top of the other. and they're at slightly different angles, so we actually make a cool little circle in the middle of that, or what looks like a circle. And what we've done is we've simply put together the save and restore, translate and rotate, and we have added that to some animation. Next, let's look at how we could shoot lasers out of our base. To start, we're going to have to track where the mouse is. The way this works is that we attach an anonymous function to the event handler on the canvas that updates mouse.x and mouse.y every time the mouse moves inside the canvas. That way we always know where the mouse is. Take a look at the code for that. So this is something new here. There was a small part at the end of Code Maven that had to do with this. But let's quickly review um, event handling. That's what it's called in programming when the program reacts to keystrokes on your keyboard or movement or clicks on the mouse. That's called event handling. You're handling an event. So we declare a variable. We call it mouse. We could have given it a different name, but this was a convenient name. And we say the variable has two parts. It has an x coordinate and a y coordinate. Anywhere I move the mouse, there is a corresponding x coordinate and y coordinate. c.canvas.onMouseMove. So that's a built-in function. And what we say is, or the format we have to use in the code is function EVT. EVT stands for event. And the event we're talking about here is the simple event of moving the mouse arrow around the canvas. Mouse.x equals event.clientx, mouse.y equals event.clientY. That says take the x and y coordinate of wherever the mouse is and store those values in the variables mouse.x and mouse.y. All right, and the rest is pretty much the same. Now let's add some code to draw a line from the center of the base to where the mouse pointer is. Look in Update, see how the line is drawn? Look at the code around c.line2. So notice how the line follows me. It follows the mouse arrow. And wherever I move the mouse arrow on the canvas, the line follows. It's able to do that because of lines 9 through 14, which keep track of the x and y coordinates of the mouse. And it's also able to do it with lines 32 through 35. Way back at the beginning of Code Maven, we saw how to draw lines. First, you begin the path, then you move to where the line begins. Here, move to W over 2, H over 2 means the center of the screen. Width, or half the width and half the height. That's right here, center of the screen. And then line 2, mouse.x, mouse.y. That means you're going to connect from the center of the screen to wherever the mouse happens to be, the mouse arrow. And then c.stroke draws the line. We can even make it so the line only appears when the mouse button is down. We just need to add another event handler on the canvas that keeps track of whether the mouse is down. See how that works? Look at the code where it sets on mouse down and on mouse up. And how the code now checks if is mouse down is true before drawing the line. Starting to look a bit like shooting a laser now. So if I move the mouse arrow around and I click on my button, I am able to shoot what looks like a laser. It's pretty neat. We're keeping track of the x and y coordinates with the same event handler that we saw last time. But what's new in this screen is lines 9 through 13. So lines 9 through 13 keep track of whether the mouse button has been clicked or not. So the default is that the mouse button is not being clicked. So is mouse down? That's false. The mouse is not down, or mouse is not clicked. c.canvas.onMouseDown function event is mouse down equals true. So the variable is mouse down gets set equal to true if the mouse button is being clicked. And then lines 12 and 13 tell us that is mouse down gets set equal to false if the mouse button is not being clicked, which would be or correspond to on mouse up. And then finally, in lines 38 to 44, the code for drawing the line is the same, but what we've added here is an if statement. Is mouse down? So is mouse down? Is that true? Well, it's only true if the mouse button's being clicked. If it's true, draw the line. If is mouse down is false, then the mouse button's not being clicked, in which case you won't draw the line. That's how this works. And we can see that clicking on the mouse button gets us to draw the laser. So far, we have a base and something like a laser shooting from the base, and we've gone over the basics of drawing, animation, and handling mouse events. Next, we'll need something to shoot at. We're going to want enemies moving in toward our base at the center. The enemies spinning as they go, and then we'll try to shoot them before they hit the base. Let's work on the enemies now. Each of the enemies should have a size, position, velocity, angle, and angular velocity. Probably some other things too, and know how to draw and move itself. We'll use objects to represent them. So this the next few parts will be like the spinning boxes that we've already done. Here is the code for an enemy object. The enemy is drawn as a box, but we could draw it as anything we wanted. Read over the code, make sure you understand it. Okay, so all we have here is really a variation of the box object that we already looked at. Here, the object is called enemy. It receives parameters. We've got in lines 11 through 14 this stuff. This .draw is a function that's defined within the object, telling us how it's going to be drawn. Now, when there's only one object, the whole object thing doesn't even, it's not even necessary. It would have been just as easy, if not easier, to just simply draw a box, right? You could have done it in a lot less code. But the reason we have this box definition here is so that we can very easily draw and animate many different boxes. And then finally here at the bottom, var e equals new enemy 100, 120, 0. Those are the parameters. And e.draw draws it. Okay, so this is kind of just a simple skeleton or framework for what's about to come. No animation or movement going on here yet, but let's play with this a bit. Can you add a few more boxes in different spots, different sizes, maybe rotate it a bit? Try to see what you can do. All right, well, take a moment and go ahead and make some boxes. All right, so hopefully you were able to play around with that a bit. With this particular screen here, I don't want you to worry about the code in lines 26 and 27. The reason for all this math here is just it's a way to fit as many boxes as you can without going outside the lines. Okay, but don't worry about it. You won't be testing on it, and it's really not even worth explaining right now. What matters here, though, is that we have drawn a lot of different boxes, and we could have changed that number. Like here's 24, right, in line 25. We could have done 34 or 44, 54, 64, 74, 84, etc. Notice that there are fewer and fewer boxes as the boxes become bigger and bigger because they're taking up more room. Again, don't worry about lines 26 to 27. Okay, it's time for you to write some code. You're going to try to recreate that enemy object on your own. Don't worry, I'll help you do it. Follow the instructions in the comments below. Write your code below each of the comments. We'll start with the object definition. So notice what she's doing here for you, giving you a lot of comments. These are like hints. And what you want to try to do is write as much as you can using only the hints, not looking back at previous lessons, not looking forward to future lessons, but just use the comments as hints and write the code yourself. Mistakes are okay. That's part of learning. So go ahead and make messy mistakes, but do this on your own and only resume the video. Pause it now and only resume it when you've had a chance to make some messy code. All right, next we need to add the member variables. When we use new, like when we say var e equals new enemy, etc., to create a new object, this function is called as a constructor. Constructor just means it builds something. And we should set initial values for any member variables of the object. Enemy has member variables for the position, size, and angle of the enemy. So we should initialize those. Follow the comments and I'll walk you through doing that. Okay, same deal. Pause, make some messy code, and then resume when you've had a chance to attempt it. Hopefully you got something like this. Now we'll add code to tell an enemy object how to draw itself. Let's start by just defining an empty draw function. The comments will tell you what to do. Add your code below the comments. So far in lines 1 through 8, I'm not explaining lines 1 through 8 because that's all stuff that we've already seen. Okay, there's absolutely nothing there or nothing new there. So I'm only going to explain things as they come up that are unlike what you've already seen. And now we'll finish it off. Follow the comments in the code to tell an enemy object how to draw itself. When you're done, it should draw something. So she is giving you a lot of hints here, right? Tons of hints. And some of those hints are pretty clear, such as line 54, where she's basically writing it for you. Okay, so again, pause the video, make a bunch of messy code on your own. Maybe it won't be so messy. Maybe you've gotten really good. But the whole point is that you can't learn coding just by advancing through lessons. You got to try to write stuff yourself. Were you able to get it? If you're having trouble, make sure you are using this.x and this.y in the c.translate call, this.angle in the c.rotate, and this.size in the c.stroke. Also, make sure you did the instructions at the bottom to create an enemy object and tell it to draw itself. So those instructions he's referring to are the ones here way at the bottom. So she's wanting you to keep trying on your own and making those mistakes. Here's what I did. So you should have been able to come up with something like this. Notice this is all a lot shorter now because the comments have been taken out. And again, I'm not going to explain a lot here because this is just a repeat of what we've already done. The whole point of the last few screens is to try to get you to write on your own code that you've already seen. Let's do one more thing. Try to create a bunch of objects. We'll use a for loop. The comments below will walk you through how to do it. Can you add the code to make it work? What you get is pretty cool. Try to do it. Well, let's see what code is being asked of us here. We want to do a for loop, and we want to start at 40 and end at 200. And then it says you're going to want to create an enemy object, and when you create it, set its location W2, W over 2, and H over 2, which centers it nicely. And then use um, I or whatever variable name you used in your for loop. Okay, so let's see if we can apply or put into code these comments. So we definitely want to start with our for loop. For var I equals, say 40, start with 40, and then I is less than or equal to 200, so we have 200 here, and increasing by 10, so I plus equals 10. Okay, so we've gotten that part done, and we need to put the open brace, and we should also put the closing brace. Okay, now we need to draw a bunch of enemies. All right, so how are we going to do that? Well, we'll do something similar to what's in line 52. We could do var e equals new enemy. And then what are they telling us here? They said location to w over 2 h over 2. W over 2 comma h over 2 comma I, right? And then we can do e dot draw to finish that off. And then we have that funky looking thing in the middle. Now we're gonna get rid of those last two lines because we were supposed to replace them. And here's what we have. What we have is we have progressively bigger boxes all being rotated around the same center. And we get something that looks like an interesting design, almost like let's see, 1, 2, 3, like a quadruple spiral staircase or something. Did you get it? I like the pattern it makes. If you didn't finish it, you really should keep working on it. It's cool when you see it. Well, we just did that. Whew, that's tough, isn't it? Coding is hard, but it's rewarding too. Let me show you where we are going. See the game running now? It is the first of 3 games we will build together. I've hidden the code from you for now. Try playing the game. When you get to the end of these lessons, you'll have coded this game mostly yourself, and you'll be able to customize the code any way you want. Ooh, look, game over. Well, let's play again. Okay, so the way this game works is you're going to have things coming at the enemy base. You've got to shoot them to make them smaller. And making them smaller means that they're going to miss you. You can also shoot them, like I'm doing with this one, until they're so small that they disappear. Okay, and there. Now when it disappears though, when it disappears, it comes back, and it comes back a little faster. So watch, I'm gonna keep getting rid of the new ones. Oh, that's a weird one. Kind of just kept bouncing on the left. And now I'm just gonna keep getting rid of that one. Watch what happens when I shoot it. Boom, comes out randomly from another spot. So, and then the score is being kept track of. You got to make sure you don't get hit though. I'm about to let myself get hit. If you get hit, it's game over. All right, well, this is your first fully animated game in JavaScript. And even though it's a simple game, it's pretty cool that you'll have the skills necessary to do animation. Now let's code that game. We'll start by adding animation. Now I've made it so the enemy objects know how to move themselves. See how it works? We animate 20 frames a second by asking the enemy to move itself, clearing the screen, then asking it to draw itself. When an enemy moves and hits the edge of the screen, reverse velocities. Okay, so again, this is a review of what we did earlier in this video. All this stuff, right? All this stuff is familiar. I explained the bounces already, explained how angular velocity gets switched, etc., etc. Nothing here is new. Absolutely everything is the same. Now, notice though, they're not really using an efficient way to create enemies, just giving it specific numbers. That's good if you want to do 1, maybe 2, but not if you want to do several. We're going to get to that in a second. But here you can see that the basic framework is stuff we've already done. We've got the animation steps. We have update all being called every 50 milliseconds. We have the bounces, etc. Because we did the work to make these into objects, it's easy to create more of them. Let's make 5 enemies all moving around. The big change is at the bottom in update all, which now moves a list of enemies and then draws a list of enemies. So let's look at that here in update all. Okay, so now this is a much more efficient way to make enemies, and that is we have a for loop. Okay, so lines 45 to 54. That's a for loop, in which the loop runs the number of times that's equal to the number of enemies. And then each time the loop runs, it sends different parameters to the enemy object, which means each time the enemy object runs, it creates a new instance of the enemy object. And since we're considering enemies as an array, each time we add a new member to the array, we can see that in line 43. Each time we add a new member to the array, we use push to kind of push it onto the stack. All right, let's change the number of enemies. So notice how easy that is. I can go from 5 to 15. I can go even to 55. And we have all of these different enemies. Now, here's the interesting thing, and it's important to emphasize this. These enemy boxes are not moving all at the same time. That is just an illusion, okay? These are getting moved one at a time, and that one at a time process, which would be very tedious for us, is happening 20 times per second. And that's because computers are insanely fast, and they do all these tedious tasks very fast. That's why we use computers. But again, I just want to repeat, this is not really animation. It's just an illusion. It's just a series of static images, and everything's happening one at a time. They're not happening simultaneously. Now that we have enemies, let's add the base and the laser back in. It's fun to see how it might all work together. See the new base class in the code? It knows how to move and draw itself, including drawing the laser. So this is now what we're doing here is we're combining all the things we've learned so far. We've got the enemy objects, which are similar to the old box objects. We have the base that we already saw earlier. How to make that base, right? The 30-degree angles. We've got the is mouse down, checking to see if something's been clicked. We have that being changed to true or false, depending on whether it's been clicked or not. We have the mouse event handler here, looking at the X and Y coordinate of the mouse arrow. We have the enemies being created in an efficient way in a for loop. And all of this has been put together into something that isn't quite a game yet, but it kind of shows us where we're going. We have a laser that can fire. We have enemies moving around. We don't have the score, and we don't have a way to be killed yet. We don't have a way to win yet, etc. But this is still the basic framework of the game, and it's all here right now. When you're learning to code, it's important to write a lot of code. Let's make sure you can create a new object all on your own. Let's start with you trying to write the base object yourself. Don't worry about shooting the laser yet. We'll add that later. This might seem hard, but be brave, try things and make mistakes. It's all good. Look for the comments in the code and write your code for the base object below them. So again, this is just an exercise in you trying to write your own code. And this is where learning depends on you, right? I'm going to ask you to pause now, but you could choose not to, and you could choose just kind of skip towards the next few things because you're in a hurry. But the problem is you're not going to learn. Or you could pause and just kind of look in previous lessons for help, or look in future lessons for answers, but that's not helping you either. Okay, just follow the comments, use those as hints, and write code from scratch. Write code from scratch. And then resume the video when you've had a chance to try it. Look at you code, very cool. Okay, now you should have been able to achieve at least some of what has been written here now, right? We have the event handlers, we have the efficient way of creating enemies, we have a way of moving the base, a way of moving the enemies, and those are just functions. And then if we go up here, we can see how some of that works, right? This dot move, and she's still putting more comments. because with those more comments, she is explaining what you have to write next. Now, I'm going to talk a little bit about some of these comments first. Okay, so like line 26, for example. Okay, this is where you need to add code. What we need to do is see if the mouse is on top of this enemy. A way to do that is to compute the distance between the mouse position and the enemy. And if that distance is small enough, we'll say this enemy is being shot with a laser. Cool, huh? Start by creating two variables below, diff x and diff y. So that just means difference in x and difference in y. The difference between the two x coordinates and the difference between the two y coordinates. Diff x will be mouse.x minus this.x. So the mouse's x coordinate minus the particular enemy's x coordinate. And then diff y, mouse.y minus this.y will be the mouse's y coordinate minus the particular enemy's y coordinate. Okay, now the Pythagorean theorem, some of you may have had this, some of you haven't, or maybe you're rusty, I don't know. But when you're getting the distance between 2 points, you can always use the Pythagorean theorem because the distance between 2 points on the Cartesian plane can always be considered the hypotenuse of a right triangle that you draw using those 2 points. Okay, use those 2 points as the beginning and end of the hypotenuse, and from that you can make a right triangle. Now, since that's true, the square root of x squared plus y squared gives you the distance, and that's because x squared plus y squared equals hypotenuse squared. And she even gives you what that would look like here in line 52 as a comment, and that's her hint for coding. Okay, another comment to explain. Okay, now there's the fun part. First, write an if statement that checks if the distance is either less than half the size is stored in this dot size as well as a local variable called s, or it is less than 10. The if statement should look like if d is less than 10 or d is less than s over 2. Using distance or dist instead of d. Oh, and that double bar, I think we have seen that already. It just means or. But yeah, I know we saw that when we did the bounces. Finally, inside those brackets, you need to reduce this dot size by 1. Okay, and we're doing that because that's going to shrink the box every time we shoot it. Isn't that great? Here's something very similar to what you just did, but the enemies respawn somewhere random after you kill them. Play with it and check out how it's done. Okay, so this particular screen has the answers, and it also has something new, which is the respawning of an enemy. Okay, so for example, let's look at this. Notice that once I shoot one, it comes back. So I'm going to shoot this, and right, it came back in a random place. Let's shoot this one over here, and look at the sides of the canvas, and notice that a new one popped out. Okay, so that's respawning. Okay, so let's look at some of the things that were added here. Now, most of these, again, they've already been explained. The exercise was just for you to write them on your own. But let's see how that works. Okay, so if s is less than or equal to 0, well, first let's go back to what happens with s. Okay, so is mouse down? Right now I'm talking about lines 44 through 48. Okay, this is where the distance between where the mouse is and where the enemy is calculated. Okay, so diff x would be the difference between the mouse x coordinate and the particular enemy's x coordinate. Diff y similar. Now the distance is the square root of diff x squared plus diff y squared. This calculates the distance in pixels, the straight line distance in pixels from the mouse to the particular enemy, or from the mouse arrow to the particular enemy. Now notice I'm shooting right here. See, if I shoot and that mouse is kind of far away from where I shot, it's like a miss. Okay, so watch, I'm demonstrating here with this one. See, I'm shooting at it, but I'm missing it, right? I'm not getting close enough to it. And that's what this distance check means, right? The distance less than 10 check is there, so it is easier to shoot very small enemies. Um, you see, if this program required me to be exactly right on the box, it would just be too hard to hit them. And so they're giving us a little bit of a buffer here. They're saying that if my distance is within half the size of the box or is less than 10 pixels away, then we're going to count that as a direct hit. So what happens with a direct hit? That's in line 57. This dot size minus equals 2. Okay, so watch. Here's a direct hit. Notice how it got smaller. Boom, smaller, boom, smaller, boom, smaller, boom, smaller. Let's do another one. Boom, smaller, boom, smaller, boom, smaller, boom, smaller. Okay, that minus equals 2 means that the size is decreasing by 2 each time there's a direct hit. Okay, now if s is less than or equal to 0, that means that we there's no point in shooting anymore because there's nothing left to shrink. And so that would jump to here. Okay, so if s is less than or equal to 0, that means that the thing's been killed. Okay, so look at this one. Okay, I'm going to kill it. See, I'm getting smaller, smaller. It's getting smaller, smaller, smaller. And now let's kill it. Boom. When we killed it, that meant that the size was less than or equal to 0 in line 19. When that's true, we then reset the size to 20. So instead of being a tiny little box now, all shot up, it's going to have its original size of 20. And then what we do is just all this here is the respawning. Okay, so how does the respawning work? If math.random is less than 0.5, okay, so there's a 50-50 chance of this. It'd be like rolling a die and you have, one or numbers 1 through 3, and then you have numbers 4 through 6. 50-50 chance, right? So math.random being less than 0.5 is like rolling a 1, a 2, or a 3 on your die. Okay, so then if that's true, well then we roll the die again. We roll the die again. And then again, we have a 50-50 chance of it being a 1, a 2, or a 3, which is analogous to math.random less than 0.5. So this dot x equals s over 2 means that the respawned object will randomly come out at the left-hand side of the screen. And then if that's not true, or if it's die numbers 4 through 6, then this dot x equals w minus s over 2. Okay, I'm going to highlight that. This dot x equals w minus s over 2. Well, that is going to be the right side of the canvas, right? The right-hand edge of the canvas. This is saying, so look at this part. This is just saying that if the first die roll is less than 0.5 and the next die roll is less than 0.5, well, then we come out of the right edge. Otherwise, we come out of the left edge. But whether we come out of the right edge or the left edge, this dot y equals math.random times h minus s plus s over 2. All this says is whether it's coming out of the right edge or the left edge, make it come out of a random part of the right edge or the left edge. Okay, now what is this else down here? This else and all this stuff here will run only if the condition in line 28 is not true. So let's say math.random ends up being, I don't know, 0.7. Well, then all this stuff gets skipped. And then what we'll run is lines 36 to 41 instead, which is saying that, all right, let's make it come out of a random place in the top or bottom edge. So this dot x tells you that it's going to be a random x coordinate in the top edge or the bottom edge. But the next few lines tell us whether it's going to be the top edge or the bottom edge. If the die roll is less than 0.5, well, then this dot y equals s over 2, meaning that it's going to come out of the top edge. else this dot y equals h minus s over 2, meaning it's going to come out of the bottom edge. Okay, so that's how the respawning works. And we've talked about how the size of the enemies, how that size gets smaller. And the rest of the stuff is all the same. We've almost got a complete game here. There are a few more things we need. We need to keep score. The game needs to get harder and harder over time. We need to detect when the base has been hit by an enemy. And when the base has been hit, the game should end. All right, so let's get to it. Let's start by keeping track of a score and displaying it too. What we want to do is create a new variable called score, make it 0 to start, and then increase it every time we successfully shoot an enemy. Then we'll have to display a score in the part of the code that redraws the screen on every animation frame. Look for comments in the code that tell you what to do. Okay, so she's pretty clear about what you need to write and where you need to write it. Go ahead and take a stab at that. Pause the video and resume when you've had a chance to do it. Now, let's look at some of the answers before we do the next thing. Okay, so look at some of the things that we added here, like with score. Okay, so if we go, let's go up here, right? Score plus equals 100, and so the score increased every time that an enemy was hit. And let's see, what was the other thing that was asked of us? Oh yeah, that's just making the score, right? So that var score equals 0 in line 3. That's the way to answer the first comments that were written up there. Okay, so not a whole lot was added with that last one. Okay, in this lesson, she says, I noticed that I never stopped shooting the laser. Do you do that too? We should make a penalty for doing that, don't you think? Okay, so watch this. See, I can hold the laser down. Right now, I'm holding the laser down. And holding the laser down means that I can just completely kill any enemy, and it's super easy, and I keep racking up the points, and the whole time my mouse button is being held. Well, that's not realistic, right? It's also not very challenging. So look at the comments here and see if you can make each fire of the laser cost something. And you're going to have to do that like here, right, in these comments. The firing on the laser has to cost you something. You have to lose some points. So think about how to do that. Pause the video, try it, and resume when you've had a chance to do it. Okay, so you should have been able to come up with something like this, right? Notice that the score goes up by 110 each time. Also notice down here that score minus equals 10 means that every time you fire the laser, you're going to lose 10 points. Okay, so watch. See, I'm at negative 10 right now. Now I'm at negative 20. Now I'm at negative 30, negative 50, negative 70. Well, why does it jump up more than 10, you ask? Because sometimes, even though you think you're clicking it once, you're actually clicking it more than once. Okay, negative 100, negative 110, negative 120, negative 130, etc. And so I'm now getting deducted for just randomly firing. This is going to teach me to choose my shots wisely and not to just keep the mouse button down all the time. Great, next let's make the game get harder and harder over time. We could do this by adding more enemies or speeding up the enemies. Let's speed up an enemy whenever it is killed and respawns. That's pretty simple to do. This time I'd like you to do it on your own. I added comments to the code that help explain what the code does, but the comments don't tell you exactly what and where to change. Can you find the spot where the enemy dies and respawns, then increases the velocity by 10% each time? Now, if you want to really make this game hard, you could have, instead of 5 enemies, like 15, and you could make it so that every time an enemy respawns, it's 50% faster. You can go ahead and play with that. Of course, it's going to be much harder that way. Okay, but for now, you can mess around with that stuff later. But for now, I want you to take on the challenge that's been given you here, and that is see if you can make the thing come back or respawn faster than it was originally. Okay, figure out where to do that and what to do. Pause the video and resume when you have an answer. Okay, now here's the answer. Let's see what happened here. Well, it all happened in lines 25 and 26. Now, actually, that's something I changed earlier. I'm going to reset here. The answer that she originally gave was 1.1. This just means that it gets 10% faster. Let's look at that in action. Okay, watch. I'm going to shrink this one. And watch what happens when I shrink it or kill it. Okay, did you see how it came back and came back faster? I'm going to do the same thing now. And watch for when it comes back. There, it came back and it came back a little faster. I'm going to do the same thing now. And then watch for it to come back even faster than the last time. Okay, now to make it really challenging, let's say 50%. So 50% means that instead of 1.1, I do 1.5. So it'll have 1.5 times the speed that it had. All right, now watch what happens if I shoot one and it respawns. Let me shoot this one here on the left. Okay. When I kill it, it comes back quite a bit faster. And now let's say I do that again. Now it's quite a bit faster. And now let's say I do it again. It's hard to do. But since it's 50% each time, now it's getting wicked fast. So fast that it's pretty hard to shoot. See? And now it's even more wicked fast. Okay, now let's imagine making the game really hard by increasing the number of enemies. So let's go down to num enemies and let's make that 15. Okay, now we're going to have a hard game. And notice that the game right now is set up in such a way that you can't lose. We're going to change that soon. So this is kind of just a warm-up. But you can see that if this were the real game, where it would say game over if you got hit, then this would be quite challenging, right? So well, let's start it over again. Okay, so pretend this is real. Well, if it's real, I gotta prioritize the ones that are coming at me because I've got too many to keep track of. And I want to avoid having them respawn if possible because they're going to come back so fast. That was a close one. Okay, so I'm kind of making sure I don't get hit. This one I'm probably going to have to kill. And I would have died with that last one that hit me. See, because with 15 enemies to keep track of, it's pretty hard. And every time I do completely kill one, see, that would have been a game over right there too. Every time I do completely kill one, the respawned one comes back really faster, quite a bit faster. Notice that all I changed here was in line 156 to make more enemies. And let's see, let's go back to the respawn part. Respawn part is up here, lines 25, 26. That's where I make the dx and the dy, that is the horizontal and vertical velocities, quite a bit faster than they were in the beginning. Next, we'll work on detecting when the base gets hit by an enemy and ending the game. Before we can do that, there's a little problem. Right now, enemies can start anywhere on the map, including right on top of the base. That would immediately end the game. We'll need to fix that. We could change it by copying code, but the best way to make a change like this is to look for an opportunity to refactor the code so everything is simpler. What probably should happen is that enemy and base objects should know how to create themselves, which would make it easier to create them at the beginning and to respawn them when they are killed. Take a look at the new code. What I did was add an init method to the enemy object. Then we use that both to create new enemies at the beginning and to respawn enemies when they are killed. See how it works? You know, it's also now much easier to make them bigger each time they respawn. Can you figure out where and how to make that change? Okay, so let's look over some of the changes here. Notice that enemy now, the enemy object in line 5, doesn't receive parameters. And it doesn't receive parameters because it defines them within the object itself. This makes it simple because not only are you going to call the enemy function when you're creating new enemies, but you're also going to call it when new enemies are respawned. When when you kill an enemy and it comes back. Everything else is pretty much the same. Notice, look what happens here in line 172. Um, since enemy doesn't have parameters, we don't need to define those parameters outside the enemy object. They get defined within an enemy object. Okay, so line 172 jumps all the way up to the enemy object, and then notice what's happening, right? The initial size, that's what I size stands for. The initial size is 20. That's going to get shrunk. This dot max dxy equals 4. So that's the maximum positional velocity, and maximum angular velocity is 8. We could have changed those to anything, um, anything we want. They could start out really fast, really slow. This just kind of gives some uniformity to the enemy objects. Okay, the other things are the same. We still have the same respawning algorithm. The randomness that takes place in lines 38, 39. And are we dead, right? This is the respawning part. And we can see how all of this works a little more smoothly. Okay, let's do the last thing we need for a full game. The game needs to end. This game ends when an enemy hits the base. When the game ends, we should see a game over and stop the animation. Oh, one last thing I wanted to explain about that last one. You might be wondering, well, how did this answer the original problem of making sure that an enemy is not generated right on top of the base? Well, okay, uh, I'm gonna restart this a few times. I want you to notice something. Do you see how every time I restart, the enemies come only from the edges? Before we made the change, that didn't happen. Before we made the change, only the respawned ones came from the edges, but the new enemies at the beginning of the game could have come from anywhere in the screen because the X and Y were random. Okay, so this is the beauty of using the same method to respawn as to create new enemies. Because notice the heart of this is lines 19 through 31. In lines 19 through 31, this is saying that the enemies will come out of only the left or right edges or the top or bottom edges. It's the only place they can come out of now. And so there's never a possibility that a new enemy will be right on top of the base from the beginning. Okay, last thing. Oh, we already said that. I'll help you out by adding the game over text and stopping the animation when the game is over, but you need to add the check the base is touching the enemy. Look for a method is hit by in the base object and follow the comments there. Okay, so notice she did give you some answers here. See, you've got the if game over, right? So if the base gets hit, game over will be true, and this will run, so you'll get your game over message. She did that. And then animation, that's only going to happen if game over is not true. So all those were added for you. Base dot is hit by enemy. If this is true, then game over is true. So that's been added for you as well, right? Well, so what is the part that you have to add? The part that you need to figure out. Okay, well, that's here. This dot is hit by. So what you need to figure out now, using her comments as a help, is um, how do you get the distance between the enemy object and the base? We've already gone over how to get the distance between the enemy object and the mouse arrow. But now we need to find the distance between the enemy object and the base. And if that distance is below a certain minimum, then it's going to be considered a direct hit and the game is over. All right, so like she says up here, spend some time on this one. Try to get it before moving on. Pause the video, do this on your own. Don't take shortcuts. And remember, the test is going to require you to make some modifications and some improvements in the game. And in order to do those, you need to understand how the game works. So this is a perfect chance to do that. You're done. You have a complete game. It works beginning to end and you did it. Great job. Play with it. Okay, so let's play the game. Oh, I might die. All right, so let's play the game. This one's slow. That's easy. This one's coming right at me, but make it smaller. Okay, game's way too easy, right? We need to increase the number of enemies. So let's increase the number of enemies. Notice here in line 46 that we have two things going on with respawned enemies. Um, in 45, it says that they're going to go 10% faster. That's the 1.1. And it says in 1.05, that means that it's going to be 5% bigger when it comes back. Okay, so you see this one keeps coming back bigger. Watch, I'm going to keep killing the same one. And notice I've got a big square here, and it's fast, and it keeps getting bigger, and it keeps getting faster. There, you can see it's bigger and faster. So fast it's hard to hit. And if I keep respawning that one and it keeps getting bigger every time, then pretty soon it's going to be very hard to avoid. I got killed by a different one that I wasn't looking at. If the one keeps getting bigger, the one that I kill and respawns, if it keeps getting bigger, it's going to be very hard to avoid it eventually. So it is possible to make this game challenging. One of the great things about having access to the code of the game is that you can make very different feeling games. Um, so this is one that here. Let's play this one again. See how it. Notice that every time you hit it, little random kids come off of it. You know, uh, like the enemies have offspring, and um, the enemies give offspring whenever they're hit, and so hitting them is complicated now because you might just be creating more enemies. And now I got to watch out for all these little ones because these little ones are going to come right at me, and then the game could be over. Now we could make this game a lot harder also by increasing the number of enemies, increasing the speed, etc. But this is just a version. Now I'm not going to spend time on how this version was made because it has nothing to do with your test, but it is kind of fun to play. Let me put it back to the earlier code for the game so you can work from that. Now you try twiddling it. Maybe add more enemies, make the enemies bigger, but the lasers shrink them faster, make the enemies faster. Okay, so this is where you need to play with it, make the little changes that you think would be cool, do the little modifications that will make this game more challenging. And this is also a perfect time to practice for the test because I will be asking you for certain things. Um, I might ask you to make them faster. I might ask you to make more enemies, or I might ask you to change colors, different things like that. Um, and oh, that reminds me actually um, about changing colors. I think I need to show you how to do that. So here's what we'll do. Let's go to the end of this of these lessons 1 through 60, and then I'll show you the color thing. Oh, we are at the end. Great. Okay, so I'm going to go back, and then I'm going to show you the color thing now, just so you know how to do it. Okay, so now I've added some color. Notice that the base is blue, the enemies are red, and notice also that the laser is green. And it's pretty easy to add color. Let me just kill these guys here, and then I'll show you. All right, it's pretty easy to add color. What you do is, let me show you I'll show you the base first. Well, let me go down to the base. Well, yeah, all right, let's go down here, go down here. Where's the base? Where's the base? New base, base, base. Okay, here we go. So line 51 or 151, C dot stroke style equals blue. That means that the lines that are used to make those little rectangles that make up the base, those are going to be blue. It's just stroke style. And then I did something similar here in line 165. Stroke style equals green. That makes the laser beams green. And finally, the enemies. Let's go up to the enemy object. I think that's way up here. Yeah, enemy, and then there's the drawing of the enemy. That's down here, yeah. Okay, so in line 106, C dot stroke style equals red, and that's why the enemies are red. Okay, so the test may involve some color changes as well. That's why I just showed you how to do this. That is it for this tutorial. That is also it for Game Maven. The next thing and the last thing for coding this year will be the Game Maven test. Good luck.